Hello, I'm Velle Toll from University of Tartu, Estonia. As you are watching this video, you know that it's difficult to distinguish between cause and effect in aerosol-cloud interactions, and polluted cloud tracks can help here. Here in these satellite images, you can see ship track like polluted cloud lines. So in addition to ships, such narrow pollution tracks could be induced by volcanoes, localized industrial sources, localized fires, or other localized aerosol sources. So ship track-like pollution tracks are typically 10 or a few tens of kilometers wide. Here in these satellite images, you can see what I call a megacity type of pollution tracks. So these polluted cloud areas are typically 100 or a few hundreds of kilometers wide. So you can see examples marked with blue crosses where these grayish brighter areas are polluted cloud areas. So first example, polluted area downwind of megacity of Moscow, where Moscow city lights are given in bright white. Then next example, downwind of Norilsk nickel smelting factories in Russia. Next one, downwind of Rotterdam, Europe. And finally, polluted cloud area induced by fires in Siberia, Russia. Now moving on to the next spatial scale. Here in these satellite images you can see polluted cloud areas induced by larger scale industrial regions. So this type of polluted cloud areas are typically a few hundred to 1,000 kilometers wide. So let's go through the examples. So again, the polluted cloud areas are marked with blue crosses, and they are given in these grayish brighter colors. So first you can see polluted cloud area downwind of Shanghai region, China. Next is polluted cloud area in the Great Lakes region, US. Then polluted cloud areas downwind of Europe. And finally polluted cloud area in the Southeast Atlantic induced by wildfire smoke from Africa. Now, comparing the properties of the polluted cloud tracks to the properties of the nearby less polluted clouds, these are the main results. We're using MODIS data, and so far we have most observations for smaller scale ship track like pollution tracks. But results really seem to hold for various spatial scales and for various meteorological regimes and various regions of the world. So in all cases we see this strong decrease in cloud droplet effective radius in the polluted cloud tracks, what is of course expected, as this is how we define the polluted cloud tracks. But looking at cloud water responses, on average there is only a small decrease in cloud water, and this offsets relatively small part of the Toomey effect. So yeah, on average we have this relatively small change in cloud water, but this really results from the compensation between cloud water increases and decreases. So in many cases we get a strong increase in cloud water, and in many cases strong decrease in cloud water. And the response depends on the meteorological conditions. So here in this figure you can see frequency distributions for cloud water increases in red and cloud water decreases in blue, depending on various parameters. So in case of larger cloud droplets, when we are more likely to have precipitation, we are more likely to get an increase in cloud water as expected from the suppression of precipitation. In case of low relative humidity above clouds, we are more likely to get a decrease in cloud water as expected from aerosol enhanced entrainment. But there's also strong dependence on cloud top height. So for higher clouds, we are more likely to get a decrease in cloud water. Overall, there is a lot of variability in the cloud water responses, and I think the process is controlling cloud water responses should be really better understood. Regarding the cloud fraction responses, we do not yet have any quantitative information based on polluted cloud tracks. But qualitatively, we sometimes see cloud fraction increases and sometimes cloud fraction decreases. Cloud fraction increases in case of closing of open cells and in case of longer lifetime of polluted clouds. So longer lifetime we see very rarely, but closing of open cells happens more often in the regions of where we have the open cells more frequently. But it remains unclear how important this really is globally. Regarding cloud fraction decreases, this happens in case of shorter lifetime of polluted clouds, but this also seems to be quite rare. Now, moving on to the polluted cloud tracks recorded in the long-term average satellite data. So Michael Diamond has this really great paper analyzing shipping corridor in the Southeast Atlantic. So here on the top left you can see MODI's cloud droplet number concentration climatology, and you can see this enhanced cloud droplet numbers in the shipping corridor. Using 1 degree MODIS data, Diamond et al. Found a small change in cloud water in the morning and strong decrease in cloud water in the afternoon. And here we are looking at the same shipping corridor but at a higher spatial resolution. So using Severi data at 0.05 degree resolution and MODIS data at 0.01 degree resolution. So if you look at these bottom images, you can really see this fine scale structure of the shipping corridor. So here are the preliminary results using high resolution data for the Southeast Atlantic shipping corridor. The method is still very simple and probably needs to be improved. Anyways, here you can see cloud water path and cloud droplet effective radius across the track. So looking at the segment, what is just 20 kilometers wide. And red pixels here are the most polluted pixels within the track center, and blue pixels are the less polluted pixels next to the most polluted area. And using MODIS and Severe data, I'm just looking at the difference between the blue pixels and red pixels here. So in some cases, as illustrated here in the left panel, we can also visually see this decrease in the cloud water in the shipping corridor. On average, using MODIS Terra and Aqua data, there is such a decrease in cloud water that it offsets about half of the Toomey effect. And based on Severe data, decrease in cloud water offsets about 1/3 of the Toomey effect. Here are a few further examples of polluted cloud tracks recorded in the long-term average satellite data. These here are AVHRR cloud droplet effective radius data at 1 degree by 1 degree grid. So we get this clear decrease in cloud droplet effective radius downwind of larger cities and industrial regions and volcanoes. So here are examples for Moscow region, Sierra Negra volcano, South Sandwich Islands volcanoes and Vanuatu volcanoes. And in all cases we get this clear spatial contrast between the polluted region and nearby less polluted region. And I think such pollution tracks recorded in the long-term average satellite data, these have great potential to help further understand aerosol cloud interactions. As the last thing, an example of using geostationary data to analyze polluted cloud tracks. So here you can see Severe cloud droplet effective radius for the European part of Russia and the Baltic countries. So again, these bright features are the polluted cloud tracks. And the red cross marks the location of Moscow, where you can see this very pronounced polluted cloud track. Using such Severe data and also MODIS snapshots, the preliminary result we have is that there is no clear diurnal cycle in the cloud water response. To sum up, polluted cloud tracks are excellent for process level understanding of aerosol cloud interactions. although it remains somewhat unclear how representative are polluted cloud tracks for global average cloud responses. But in my opinion, the polluted cloud tracks still have a great potential to even further help to improve our understanding of aerosol cloud interactions and to help us answer many more research questions. Thank you.